Yeah, good morning. In this lecture video, I'm going to explain uh, program to add 8-bit numbers, that is 8-bit additions. So, how we can perform addition of 8-bit numbers. See, one question is appeared in the exam. Okay, so write an assembly language program to add two input data of 16-bit result. That means to say we are adding two data of 8-bit numbers and its result is 16-bit. This result is 16-bit in three different addressing modes. Three different addressing modes. Right? So we are adding two input data of 16-bit result. So that means we are adding two 8-bit numbers and the result is 16-bit, more than 8-bit. Let's consider one example. Let's consider example 89H and FFH. So if we add 89 and FFH, so manually first we add low digit, that is 9 plus F, that is 15. So 15 plus 9, 24. So 24 in hexadecimal it is 18. So 8 is result, okay, and 1 is carry. Now this one will be added to 8, that is 9 again plus 15. 9 plus 15 again 18. 24 in hexadecimal is 18. So 8 and 1 carry, and that carry is considered as a more significant digit. So to represent the number in as a bytes, we consider this as a 0 1, that is I byte result. I byte. So now the result becomes 16 bit. Result becomes 16. So the best example to understand this concept, program to add two input data of 16-bit result. So this is the 16-bit result. Clear now? So this has to be implemented in a three different addressing modes. So first we'll consider immediate addressing mode. So as you know, in immediate addressing mode, operands are specified as a part of an instruction. Here the operands are the numbers 89 and FFH. So first we'll say move a comma hash 89. That means first number is copied to accumulator A. And then add a comma hash 0FFH. 0FFH. As I said, if you give FFH directly, you will get an error because assembler get confused whether F is an hexadecimal digit or it is an alphabet. So that is why 0 is prefixed. Okay, if it is, if hexadecimal number starts with an alphabet, it is prefixed with a 0. But here it is not required. Here it is not required. Okay. Then it performs content of A added with the FF, immediate addressing. And even the question they are not specified where to store the result. We'll store the result, low byte result, that is in A into R1. Store the low byte result in R1, and I byte result is always 0 1. As we observe now, I byte result is 0 1 always. So 0 1 will copy to R2. Store I byte result in R2. End of the program. So this is a simple program using immediate addressing. So one way. And second way, we'll consider direct addressing mode. So direct addressing mode means the operands are present in memory and addresses is known, and that addresses are specified as a part of an instruction. So first we'll consider the numbers are stored at the addresses 20H, 21, 22 and 23. We store the result. So if you consider the same example, it is 89 plus FF plus means that result is 88 low byte result and I byte result is 0 1. Correct? So let's see the program. Start with the 00H. Move A comma 20H. First number is at 20H. No, that is copied into A. Then add A comma 21H. That means second number is present at the location 21H. Add with the 21H. Okay. Then here we specify store the low byte result at 22H. So move A 22H comma A. Store low byte result, and then I byte result, that is 0 1 into the location 23. So move 23H comma hash 0 1H. Store the I byte result at 23H. This is the end of the program. Clear now? So this is using direct addressing mode. So second way. And third way, we'll see indirect addressing mode. So again, indirect addressing modes, the operands are present in memory. Addresses are specified indirectly. That means we use a pointer registers. Okay, so this is the memory view. 28 contains 89. This is not 88, this is 89. Okay, and FF, and the result will be 88 and 01H. Okay. So let's use or not to point a number. I mean, uh, first number that is at 28. So or not is pointing to the location 28. So get that number into accumulator using an instruction move a comma at R0. That means first number at 28 is copied to accumulator, and then increment the pointer to point the second number to be added. So increment R0. So R0 is pointing to this location. Okay. Now say add a comma at R0. Now a having first number and R0 is pointing to the second number. So it performs addition of first number and second number, and the result will be in A. That has to be stored into the location 22. No, again increment R0 to point to the 22. So increment R0, so it is pointing to 22. Then store the low byte result using an instruction move at R0 comma A. Store low byte result at 22H. Okay. And then again increment the pointer. It is pointing to 23H, and to this location we need to store I byte result, that is 01. So move A comma 01H, then say move at A at R0 comma A. I mean first we copied A with the 01H, and that is copied to the location pointed by R. This is the end of the program. So this is the third way using indirect addressing. Okay. Now we'll consider one more question appeared in the exam. What are the final numbers in A, B and overflow after the execution of this instruction? So this is a simple instruction. Let's analyze this. So these are the instructions. So as you know, first instruction move data. Okay. So 7B is an immediate number that is copied into accumulator. And then see here 0F0. It's supposed to be H. It's supposed to be H. Okay. So it is the address of B register. So B register is copied with the 02. So B is equal to 02H. And next instruction they are telling mul AB. That means multiply the content of A and B. Now the content of A is 7B into 02. So it performs the operation 7B into 02. So the result is F6. Result is only one byte. Only one byte. That is stored in A register. That is stored in A register. And B is equal to 00. So overflow is set to 0. That means the result is 1 byte. Okay. And then say move B comma hash 0 FE. So FE is the number. So B becomes FE. B becomes FE. And the next instruction is mul AB. So now A is having F6. That is the result of multiplication of 7B and 02. And B we just copy FE. So it performs the multiplication of F6 into FE. F6 into FE. Okay. So it becomes the result F4 and 14. So 14 is the low byte result that will be in A register, and F4 is I byte result that will be in B register. So after execution of this instruction, A is equal to 14H and B is equal to F4H. And observe here, overflow is set to 1. So important here, what are the final numbers in A and B and overflow? Correct? So here overflow is set to 1. It doesn't mean an error. It doesn't mean an error. It indicates that result of a multiplication is more than 8-bit number. More than 8-bit number. That means it has 2 bytes, low byte and I byte. That I byte result is present in B register. So we have to analyze B registers. Okay. So after first multiplication instruction, overflow is 0. Since the result is 8-bit. 8-bit. But after second multiplication instruction, overflow is set to 1 because the result is more than byte value. So this is how, yeah, fine. So A is equal to, so final numbers in A, B and overflow is 1, 4, B is equal to 4 and overflow is set to 1. Okay. So we'll continue in the next video. Thank you.